chat for any technical problems during that. But without any further ado, I hand this off to Dr. Jim Rickles to introduce our speaker today.
Okay, thank you, Tommy. So my name is James Rickles. I'm actually the director of the NHERI Lehigh experimental facility. My co-director, Professor Claudia Reich, she's actually online. She'll be also perhaps asking questions, if not answering them, right, Claudia? So what I'd like to do is to first give you a little bit of an overview of the purpose of our series. We want to create a forum, and the reason for the forum is to present ongoing natural hazards research, including that which has been conducted at Lehigh or will be conducted at Lehigh, and it's basically many different subject areas, including fluid structure, multi-physics type, soil structure, fire, standard structure, response modification devices, and today you'll hear another aspect which I won't take any thunder away from you from the speaker, so I won't say anything about that. I'll let the speaker introduce that. The other aspect of the forum is it creates a forum for the audience and also the researchers to hear and present their research, and to perhaps also develop some collaboration. So the more people you know in your topic, the more you can connect and be successful. We try to have these seminars during the semester when people are basically in their office or at their institution. So about once a month, and we announce these through the NHERI Design Safe. So hopefully all of you received that invitation. If not, then you found out some other means. Anyway, about once a month. And this will be recorded, and we have it archived on our website. So if you Google NHERI Lehigh, eventually you'll get to where our experimental facilities website is under Design Safe. You'll find the description of our facility, the leadership, I guess, the projects we have, but also the archiving of all the seminars going back, I think, 4 or 5 years. Now, the other thing I want to mention is a little bit about NHERI Lehigh. So we're an open access facility for researchers who conduct really cutting edge research, and we really do computational and experimental and combine those in one setting, and that's called hybrid simulation. So we try to do that in real time, multi-directions, multi-physics, and this is something that appeals to researchers, but it's not the only thing we do. So you hear some other things that a researcher who's been using our facility will talk about, and that person's name is our speaker, Islam Mantawy. Islam's an assistant professor in the Department of Civil and Environmental Engineering at Rowan University. Very important, he's a registered professional engineer in the state of Nevada, so I'm sure he brings that practice into the classroom. I know he does that in his research. So in terms of his research, he has two areas that, amongst his areas that he focuses on, those two. One is the concrete additive construction, and a little bit of distraction here, it's okay. Metal additive manufacturing. And then, so there's two, there's the concrete and there's the metal additive manufacturing. So in terms of the concrete, the former focuses on topology, optimization, optimizing the layout, construction, the reinforcing techniques, that's very important in concrete. Hazard protection systems, functional graded structures, and adaptive and reconfigurable structures. So we're trying to make things more sustainable, more resilient. Some similar interests in additive manufacturing in metal, but it also includes repair and strengthening through what's called cold spray and hazard, as applied to hazard protective systems. Now, Dr. Mantawy is very active also in the profession, so he's a member of ASCE as well as the Structural Engineering Institute and a member of the American Concrete Institute. So you do metal work, but you're not ASCE, so we'll have to AIC. We'll have to ask him about that. That'll be one of our questions. So today's topic is transforming seismic systems through concrete additive construction and metal additive manufacturing. So with that, I'm going to welcome the speaker and have you take the podium. Thank you.
Thank you. Thank you, Dr. Rickles, for the introduction. So today's presentation, my layout today for this presentation, I'm going to start with the motivation. introduction and overview. I'm going to spend some time on the background, giving the attendee background on what is concrete additive construction, what is metal additive manufacturing. We can call it 3D printing for short. And we will introduce my laboratory at Rowan University, Additive and Robotic Construction Laboratory, to provide an overview. After that, we will jump in two projects here. The first one is related to using concrete 3D printing or additive construction for new seismic protective system. And the second project is additive manufacture seismic metal fuses for concentric brace framing. And at the end, we'll have an open discussion on the potential on rules of advanced manufacturing in natural hazard mitigation. So starting with our motivation here, I always use a couple of slides to break ice. And I always say, if you can spot differences between the left photo and the right photo, the left one is the construction in 1950. The right one is the construction right now. I may be asked here in person, what would be the difference between the two photos? If you can spot difference. Let's see, Liam here is doing no difference. There's slight improvement in tools and equipment, but I think it's only black and white. This is for a concrete side, but from the metal side, I also did some search and find that this was actually 1940s and 21st century on the way we do make our steel. So steel making. And you can see here that we're line big furnaces, and there is a development in this industry using electric furnace to reduce carbon emissions. But I just want to make sure that we are doing the same business over almost a few decades the same way. And my presentation is not intended to have replacement of those methods. It's just introducing a new construction technique, new manufacturing technique that could go hand by hand and solve problems that exist in conventional way of making steel and producing concrete structure. So in the background, I want to be able to have the audio engage with me. So I'm using ISO ASTM 52900 for additive manufacturing processes. You can see here, ASTM recognize only 7 techniques. The first one on the left side, top left side, is steel lamination. It's basically gluing and with adhesive steel sheets to build your structure. The second method is metal extrusion, and this technique is actually suitable for concrete, metal, and polymers. And for binder jetting, basically using the powder on the bed and using additives or binders to glue them together. This also is suitable for concrete, metal, and polymers. Metal jetting is mainly polymers. If we keep going, powder bed fusion is metal polymers, and there's different processes like direct metal laser sintering, selective laser sintering, selective laser melting, electron beam melting, and selective heat sintering. The other technique here is that photopolymerization that is mainly for polymer using UV lights for curing resins. And for metal, there is also direct energy deposition, which is WAM. We have learned a little bit today about WAM and EBAM, which is electron beam additive manufacturing and big additive manufacturing. So in this presentation, I'm going to focus on extrusion to extrusion for concrete and for metal, direct laser sintering. And we will learn a little bit about what are additive manufacturing. So what are advantages of additive manufacturing? We can actually reduce labor need, enhance labor skill set, time saving, reduction of material wastage through topology optimization, broader design creativity and problem solvability, a reduction of carbon footprint because we produce now more optimized structure. We're not wasting material where low stress region. It also could introduce on-demand manufacturing. So if you have a hazard, you can actually print element to respond to this hazard and also provide a competitive economy and businesses, especially small businesses. So I'm gonna be changing between concrete and metal, so please pay attention with me here. So the first one is concrete additive construction. Our lab classified the construction technique into three techniques. The first one is conventional construction. We use that for decades. So using formwork, placing reinforcement, casting concrete, strip formwork, you will have a structure. Most of the technique that we have right now for 3D printing of concrete rely on using what we call hybrid construction. So basically you 3D print shells or forms, placing reinforcement and post-processing casting. What we try to do at our lab is to have a complete inline process where we can 3D print or additive construct structures with inline reinforcement and also using topology optimization to create compression-only structure and tension-only structures. So as we know, concrete for years require good slump and vibration to fill formwork and also encapsulate reinforcement. However, in 3D printing concrete, we have to alter the rheology to be able to print and build object layer upon layer. And those actually, as you can see here in the video, we're able to print square. This is not for a structure application, it's mainly for material development, but there is a lot of challenges in this process. The first one, you will be able to get some collapses and learn from the collapses. The material is fresh, gaining strength over time, so there is buildability failures. There is also shrinkage problems, crack due to shrinkage, and also edge cracking. So now we think about having the entire structure or element exposed to the ambient condition. It's not in formwork anymore, so shrinkage problem is different. A scale at this technique. As Dr. Rickles mentioned earlier, reinforcement is a bigger challenge in this industry because we always think of reinforcing the same way with the same rebars and stirrups, while we can have alternatives because those actually were driven by formwork. And also have interlayer bond issues and anisotropy that reduce due to the layer by layer nature of 3D printing. So you basically could have material properties changes from X, Y, and Z directions. I'm going to jump back to metal. Here is the most common technique using arc wire additive manufacturing WAM. So as you can see here on the left side of the slide, the video is showing the process. The process is basically a wire that is melted down and continuously welding the object. So it's basically, you can call it like continuous welding. So we need to prepare the path for printing, deposition, welding. You have to do a lot of thermal management and post-processing. As you can see here, you can see a lot of layers. And now we can have a fatigue issue. We can also have a corrosion issue. And also we have the steel now as a kind of anisotropic material. So just to give the audience the state of the art in WAM, here I'm showing some work from Dr. Laurie Gardner from Imperial College London, where he spent almost 1 decade researching WAM from a small scale tube testing and dark booms in different directions to use in mid-scale where his team is using WAM to strengthen existing structure and improve the buckling behavior. And recently, they published a paper on the first bridge that was 3D printed in Amsterdam, Netherlands. However, in our lab, we actually try to facilitate powder bed fusion, which with the technique called direct metal laser sintering in a structure application. As you can see here on the video on the left side, we can create objects using powder, metal powders, and laser to sinter the layer as we intend. As you can see here, an object is melting or sintering inside the printer, and you can keep building the structure layer upon layer. The only challenges big challenge in this technique actually is that build volume. The printers are limited in size. Even now, there is a lot of advancement. I was able to discuss with the company that now we are able to print like 5 feet by 5 feet by 5 feet objects. So the technique here, we have 3D models for sure, powder bed preparation, and using ruler to slide the powder, using laser for sintering and melting, and building layer by layer. The layer heights in this technique is the height of, or actually the particle size of the metal, so it's like 40 micron, and it also may require post-processing like heat treatment. So here is the factor that could affect mechanical properties. For sure, the powder used, we can use stainless steel powder, you can use titanium powder or nickel. The laser power, the scanning pattern, scanning speed, layer thickness, bead blasting, and heat treatment. However, that also have impact on ductility, ultimate strength, modulus of elasticity, yield stress, anisotropic behavior, and fracture toughness and thinness. So here's I'm done with my background. So I'm going to spend some time on introducing our lab. So our lab here is myself. I have 4 PhD students in our group. Jenna is working on topology optimization for both concrete compression only and tension and compression structure. Anthony is working on a rocking system that we're going to present today. Ali is working on a very nice project developing material for in-air and underwater 3D printing. Hamdi Farhood is working on all the steel-related research in our laboratory, from 3D printing or additive manufacturing and other non-additive manufacturing application. And Zain Hanoun is master student working with us on developing material for 3D printing. So our lab focuses on 2 research areas. The first research area is, as I mentioned, concrete additive construction. A lot of work in topology and structurally and topology and structural optimization, developing hazard protective system, lower carbon concrete material, lower bonded carbon, inline reinforcement technique, and multifunctional structure. In the metal side, we work on topology optimization, hazard system. We also have at Rowan University cold spray laboratory. We work in collaboration with chemical engineering department to repair corroded steel structures, and a research area that we are starting very soon is material printing. So I will not spend so much time on how we develop our material. I'll demonstrate it's printable and meet the standards. So what we do in the lab, we do, as you can see here, if you have this flow in regular concrete, you might not accept it, but for 3D printing, you want to print layer by layer. So we do a lot of tests on using floating testing, setting time to identify the window that is valid for printing, a lot of compression testing to verify the material as cast, as printed, a lot of tests for the extrusion of the material and extrudability, buildability, where we test ability of the material to keep its shape and retain its shape without failure. And as you can see here, how it looks like as a material is a fused layer from a cross section that we cut through the material. And you can see the layers all from the outside, but it's really fused with the technique that we use. And we are very happy with the product. We also collaborate with Dr. Trias from Rowan University on using LiDAR to capture geometry and identify cracks as we print. Here are the systems that we have. We have 3 different systems. We have a printer it's called SCARA Elite Roadrunner. It can print 20 feet by 7 feet by 7 feet print volume. So it's about 6 meters by 2 by 2 approximately. We can use small tubes to print very small cylinder elements. The nozzle 8 millimeter on the left side. In the middle, we also have another system that can enable us to print from 8 millimeter up to almost 1.5 inches. And we have on the right side here the 3D printing with full utilization of the equipment using the pumps that we have in our lab. So basically, the right side is where we use the pump. We also develop materials. We actually realize that material is brittle, as concrete, as you know, always. So we incorporate fibers into the material, steel fibers, different lengths. we were able to print with 4.5 millimeter, 6 millimeter, and up to 12.7 millimeter steel fibers. So as you can see here, printing on the square, we are using the square as a benchmark for cutting sample, testing cubes and flexure beams, and make it like a standard for the quality of the print. We also take a pride of the quality of our prints too. We also print in slopes, and I'm going to mention why we're printing in slopes, because we claim that this method is fault-free, so we can now have the geometries. So here is a pyramid that we printed. It's a 12-inch by 12-inch pyramid that, as you can see here, was a vertical slope, from a vertical position around 26.5 degrees. And this one was actually printed with fibers too. We actually were able in our laboratory to print in slope up to 50 to 55, even 60 degree slopes from vertical position. You can see here we start from the base, almost zero slopes, and gradually changing the slopes as we go up. And as you can see here, a lot of material is still fresh, take like 60 minutes to start setting. So a lot of challenges as we print, and a lot of deformation that happen in the layer that we don't see, but it's micro scale. And as you can see here, able to withstand the load, especially the first few layers have smaller dimensions. We actually test also what's called stress testing. So we print until we fail to understand the material behavior. So as you can see here, we keep printing on a slope, and this one, if you can take a tangent at the end, is almost like 65-degree slope, but with a lot of deformations on this overhang. As you can see here, the material is like hanging on the air almost, and now there's like a fight between the material trying to collapse and try to hold itself, and that's actually the slope that you can say it's a safe slope to print. As I mentioned earlier, for next slide, but for this one, we try to 3D print the freestanding arches. So basically, we are segmenting the structure, 3D printing both sides and connecting them with the slab. As you can see here, we 3D printed two piers with a constant slope of 45 degrees, which is a safe slope for us, and using the top slab to connect them together. We also have research that started as idea in November 2023, where we actually tried to 3D print underwater. So the idea here is to 3D print in water tanks and understand the material behavior, interaction with water. There's a lot of challenges, use more than in air. You can say that water buoyancy can help reducing the weight of the structure, or like the gravity inside the material. But there's a lot of interaction because concrete is cement, water-based also material that interact with water, and there's a lot of washout that happen. So here is a video that was showing for 3D printing underwater in a water tank that we did in 2023. And the idea was to print underwater and off water, and there's a lot of application for that. Bridge casings, repair, and even artificial reefs on the water if needed. So you can see here, we just jumped the video at the end, and we are able to print underwater and off water our structure. I don't want to spend like 2 minutes watching this video, but at the end of the day, you can see that the same material is extruding underwater and off water. So we have a active research area on understanding material behavior underwater and off water for new wave flow construction. So I think this is enough prerequisite material to start the actual two projects that we're trying to start here. So the first project is seismic protective system with 3D printing or additive construction. So we are familiar with the resiliency diagram. On the left side, you can see the functionality of any structure. Horizontal axis is time. So you may have 100% functionality, but you may have an earthquake or a hazard or disaster that could cause damage and functionality loss. And the residual functionality, we call it robustness, and the time needed to mobilize equipment and resources is the limiting factor, and the time needed for repair, we call it the repair time, and the ability is actually the summation of 2 times, time to prepare for repair and starting the repair. So there is a function here. It could be a linear, it could be at different slopes, functions until you go to the end of repair, and you can target 100% functionality recovery or a percentage of it. And this diagram here, the big diagram here, we call resilience loss indicator. So the bigger is this diagram, meaning that you need more time and you have more losses. So our goal actually in this research area is to create seismic resilient system that actually have less functionality, so you can have more robustness. That translates also to less repair. So flashback from 2014, during my PhD, we did experimental work at University of Nevada, Reno. This project was a collaborative project between University of Washington in Seattle and University of Nevada, Reno, where we developed a rocking system for bridge application. It's a precast column. It's pre-tensioned, so precast and pre-tensioned. And as you can see here, the green lines in the middle are the possible pre-tension strand. We have a column end with rough surfaces that have later on cast concrete around it for a socket connection. We also have end tubes to protect the concrete from spalling. We also have unbonded rebar for energy dissipation through yielding as the structure rocks. And the top connection was reduced concrete suction to accept the end of the pre-stressing. The rebar was also connected to the cab using holes that was all grouted together. So the system relied on the post-tension pre-tension to self-center, while the rebars to dissipate energy, but it was internal mechanism using yield. As you can combine in the moment rotation curve, you can achieve self-centering. So we compared the system to a specimen that was tested in 2004 as conventional bridge system with normal design, and we observe a lot of concrete damages, rebar exposure, buckling and rupture, and because we actually shifted the behavior from flexure buckling into a rocking behavior. So here is the specimen at University of Nevada, Reno, 72 feet long bridge, quarter scale. As you can see here, we are actually using this ground motion 2.3 times Northridge earthquake, and we're able to, as you can see here, the bridge is rocking back and forth on predefined interfaces between the columns and the foundation, column with CAD. There will be a zoom in view in a few seconds to show you how it rocked back and forth. And after earthquake, you can see how vertical and plumb the column is compared even to the background steel frame. As you can see here, the rocking is back and forth, and thanks to the pre-tension pre-stressing that bring everything back. We face a lot of challenges in aftermath of this testing because a lot of ruptures happen in the rebar that was not able to inspect because everything's recentered off nicely. However, as you can see here, the tubes actually is preventing the visual inspection too. So we, as you can see here, the only crack that happened to the column was at 12 degree in percentage drift ratio. It rocked on the surface. The foundation also got some cracks and spalling due to the rocking motion. The steel tube at the end had a bulge due to the high dynamic loading. We also have a big challenge here where after we saw cut, we actually know that the rebar fracture from the sound as they fractured during the test. We did a lot of tests like post-processing using low cycle fatigue and acoustic emission to identify the fracture. However, we tried to verify that, so we saw cut all the connection, and you can see here all the outer rebar fractured, and that was a really big setback because we try to make sure that we can have a resilient system that resume functionality quickly. It was good for purpose of emergency vehicle because the bridge is still standing. However, after recovery, you have to replace it. So we thought, can we enhance the system So first, we tried to study different systems for seismic mitigation and bridges. The first one is rocking system, as we discussed, and building the use of damper, either liquid damper or friction dampers, and also the famous seismic isolation, which basically shifting the build of the structure to reduce the acceleration of the structure. We thought, can we actually get the benefit of all this technique using a new system that enabled by 3D printing? So we also thought of bioinspiration, a way that we have our joints. The first one is shoulder joints. You can see here a lot of curvatures and a lot of ball socket connections to allow the free movement and mobility. One joint here, as you can see, hip joint and rotational in all degrees, and it enable mobility. And also, as the socket and ball connection, as you can see, also you have articulate cartilage, which actually a tissue that is soft to dam the movement. We actually in our body don't like friction because it's painful, but we can actually use the same concept and be inspired by those to build a new structure system. So here, what we try to do as one directional loading first. So we try to have 3 additively manufactured of construction rocking columns, was post-tension and not pre-tension in this case, with unique end design that based on concave surfaces. We can explain why we are doing that in a moment. By positioning a damping material, being inspired by joint, we can also achieve damping of the forces and energy dissipation to substitute internal rebar. We also thought of using external energy dissipation based on rotational friction. So as you can see here, the finished change we have is that the foundation and cab has to be capacity protected, no cracks, no spalling. So we get some cracks and spalling, this mainly because of the way that rocking on a cylinder element or cylinder that rock back and forth in one point or a corner. So it concentrates a lot of stresses on one point and result in cracks. So our solution was to actually 3D print the column with end design that has concave surfaces that enable generating the surface as a rock opposite to a point concentration. So the column will be additive reconstruction post-tension rocking column. As I can explain here quickly again, as we rock back and forth, every moment of rocking, you have stress concentration at those 4 points. And our goal is as we rock, we're able to have like a double concave surfaces with different curvatures. So as the rocks, they meet together and create a better distribution of stresses on the foundation. That's actually also what we have on our shoulder joints. For the internal rebar that fracture, we thought of using different techniques. It could be one of those, or it could be also a combination of both. The first one is basically using damping material that could be rubber material or even high density polyurethane to embed it in this gap. So as a truck, it allows deformation, but also dissipate energy by deformation. And one example here, as I mentioned, high density polyurethane, where we have a very low stresses, almost 30 psi, similar to the tire pressures that we have, but it maintains this force based on the vertical strain for up to 45%. The second technique is external elements using rotational friction. It's assembled in a king configuration or deformed configuration. So as it rock back and forth to enable energy dissipation by rotational friction. And this is also similar to what we have on our hip joints. And we, in fact, conducted a test a couple of years ago here at Lehigh University on those small devices. As you can see here, we tested on the belt configuration, and this one was only to test the compression side. So we don't have individual tension or straightening of this element, And you can see here we have very reliable cycles of energy dissipation. For the 3D printed column, we designed the column, and as I mentioned before, we're able to take advantage of free geometry to create the socket connections of the end design. So we're able to actually do 3D print this column. And I'm just in this research, we are in a stage now of testing the joint itself. So we 3D printed this one, and the video here is showing quarter steel half, sorry, quarter you have you 3/4 and the end. I won't spend so much time on the videos, but here is the end of the printing. You can see here high quality print, hopefully you can see, and we're able to finish the print for this scaled connection. So our goal now, we understand that what I presented before was like the column sitting on the foundation. We really need shear block to block the shear movement. So what we have done here, we brought the column into the foundation, and we will be continue constructing this specimen and testing at Rowan University, and hopefully the full scale event Lehigh sometime in summer or fall, hopefully. So the second project is we are using metal manufacturing. We're using developing new seismic fuses that can be part of concentric brace frame and other brace systems. So here, what we are going to switch from concrete to steel. So a special concentric brace frame. You see those on West Coast for a lot of building. They provide stability as we construct. However, they in seismic movement of the ground motion, the diagonals in the brace frame dissipate energy and act as bigger fuses. So the yielding compression, so it's yielding tension, the buckle compression, and they could eventually fracture due to low cycle fatigue. On the top right side of the slide, I'm showing the test done at the University of Nevada, Reno, 2019, for long duration effect on concentric brace frame, and the research revealed that with lower number of with long duration, you could expect the fracture to happen earlier due to low cycle fatigue. Our group works in verifying numerical models for existing tests that our previous tests done in the US. So what we thought about this is, instead of having a very long bulky element here, which is the brace that we need to repair or replace, or eventually replace the building because of the damage, because we cannot repair the building. Could we actually segment this into 3 zones or 2 zones where we enlarge the outer element here, as you can see, so we keep them in capacity protection, so no yielding, no buckling, while we concentrate or localize the damage only on those fuses that in red color. And we went through topology optimization and structural optimization processes to size the fuse so that we achieve the same energy dissipation, tension, and compression, and system stiffness as the original concentric brace frame. And as you can see here on the right side, I'm showing the stiffness for both one brace and what we call hydro brace. So in a system, what you can expect on the lower side of the right figure, you can see that one brace alone dissipate in this manner as a yield and tension, the buckle and compression. The brace itself as a system is symmetric because every brace changing tension and compression depend on the direction of the ground motion. However, the top 2 options that we have here, we have a two design. One is double funnel, other one is C design or cylinder design. So our goal here is to create those fuses that emulate the same behavior of the brace, protecting the part of the brace and enable replacement of those fuses after earthquakes. Those fuses, with thanks for metal manufacturing and thanks to high steel alloys like 74 pH stainless steel, with higher strength enable us to much further reduce the length of those fuses. Because if you want to do it actually for a normal steel, it's going to end up to be the brace itself. So in this project, we move from topologies and structural optimization, a lot of numerical simulation, to finite element analysis using our software to size the fuse and verify the fuse. We're also in collaboration with industry, we are able to 3D print fuses and testing them. And hopefully, in the part of this project, we'll be testing the hybrid fuse. So this process starts with for any optimization, identify objective function, which is minimizing the strain energy on those fuses. And our design variables, the material is different, the shapes are different. We have constraint, equality, and inequality. And we also try to get to reduce the volume of our material. So here we can see the process of stages of optimization. We end up with this shape, which is on this red box on the right side. And we further enhance it, make it printable friendly using this double funnel design. However, also we can come up with this different design that is cylinder in shape with vents and opening that enable this vents and plates to buckle. So basically, we are using the buckling theory, another theory to just get those plates with those materials to buckle in the same way as the bigger, larger elements or bases. So as you can see here, we have 5 different numerically experimented or tested specimen. The first one is just a regular conventional exercise of praise. Second and third are the hybrid one in the middle, either double funnel or cylinder fuse. And the other ones is just the cylinder fuse itself by tension pushover, pressure pushover, and cyclic loading. So in tension, as you can see here, our hybrid systems surpassed the conventional, but we still under the limit of the capacity protected element and outer element, so we are in good shape. In the compression side, we really get really close to the compression capacity of those conventional ones. Under cyclic loading, you can see on the left side the energy dissipation for the 3 systems: the conventional one, the hybrid brace with double funnel and cylinder elements, and the energy dissipation numbers on the right side of this slide. And we're able to get a technique that we can further optimize our fuses to achieve whatever energy dissipation we target. So a lot of numerical has to be verified with some testing. So we did actually test small design, like scaled version of the fuse. This fuse was fabricated or manufactured, using metal powder bed fusion, using direct metal laser sintering or solidification. This is a printer EOS M290. And as I mentioned before, the particle size of the powder is 40 micron. And the material that we used is EOS 174 pH stainless steel. 17 is for chromium content and 4 is for nickel content. So this is how the material stainless steel is defined for the pH stainless steel. We also did heat treatment after the printing up to 900 Fahrenheit. Here is the stress strain curve for the material that we use for both, especially for numerical simulation. So stress at 0.2% is around 170,000 psi. Tensile ultimate strength is 190,000 psi. Modulus of elasticity 28,500 psi. And here I'm showing the specimen. The specimen height was only 2.5 inches, and the weight 50 grams. And the thickness of each plate was around 1 millimeter. And I want you to guess how much in compression this specimen carried. It carried 81,000 times its own weight. It carried around 4,500 pounds. I'm not sure how many elephants is that. It's like the elephants on top of those. So So the process itself starts with preparing the build plate for the MLS process using the powders that we use, 74 pH stainless steel. And Rowan continuously going after you center layer after layer. As you can see here, this small dot in the second figure from the left on the bottom side, showing you a solid dot, which is actually the outside circle perimeter of the bottom and top side of the double funnel. On the right side, top right side, you can see here a mountain of powder that is, the specimen is embedded in, and you have to excavate to get the specimen out. The specimen now is detached from the build plate, undergoing heat treatment to up to 900 Fahrenheit, and after that, bead plasting to make it look like steel. It is a steel, okay? The steel is stainless steel, and it's we tested that specimen at Rowan University and using a monotonic loading and compression to make sure that the behavior is stable after buckling. So as you can see here, we achieved 4,500 pounds, almost 4,500 pounds in compression. For this particular design, the double funnel, one funnel buckled before the other one. This due to the imperfections that happened during the process. Some of the powder maybe not centered completely. So one side always going to be stronger than the other side. It's actually inspired us to do the cylinder design because we don't want to waste material too. But since we have the specimen, we decided this is actually the force displacement curve. On the right side, I'm showing a slow motion video that shows the buckling of those plates as they happen. It's very satisfying to watch, to be honest. Sometimes when I have stress, I just open this video and watch it. You can see the lower three plates are deforming, buckling, and all those plate buckling capacity is actually what we try to mimic in the large brace or conventional brace. And when we finished, we decided that we actually machine the specimen, reclaim the undamaged part, and test it again to verify that the undamaged part is stronger. And we tested that, we achieved around 4,700, so it's around 5 to 7% increase. And this also translates to the quality of the printed option. You don't need to have one side very stronger than the other side, but you can either have them fully synchronized with strength or matching the strength either. So we did a lot of numerical simulation using Abacus. We're still on the verification side of it. This is the blind prediction before we start doing the iteration. We get the behavior. We still are stiffer in the numerical models. There is a lot to do that we're trying to do with the digital image correlation data that we gathered during the test to try to actually model the material, because what we used is just a stress here that is for this material. Our goals is to actually test those braces. As you can see here, some of the specimen that's fabricated, and we will be able to soon in this summer to optimize the fuses, place the fuses in the middle of the end, testing the hybrid system, and hopefully protect the outer element and localize the damage in those fuses and replace them. After earthquake, those fuses also can be melt down, reclaim the material, and reuse for other applications. So there is also eco-sustainability component to that too. And you think now of an earthquake that you need to replace those elements, you don't need to have a stock of them ready. You can 3D print on demand. So this is the end of the second project. Both projects are ongoing projects. So, and I think there is a potential to continue even for more years with more research and more testing, for example, for hybrid simulation and cyber physical testing too. Here I'm just trying to end this presentation with open discussion. Instead of you guys asking me, trying to ask here, but you will have a chance to ask me anyway. So here I'm trying to say, like, what are the potential and opportunities for advanced manufacturing in mitigating natural hazards? So I thought of some of those before this presentation. One is we have the wildfires in Los Angeles, right? So the wildfire, the way it's initiated, that we have wood houses that actually go to the fire and transmit the fires to another house and this propagate, right? Can 3D printing of concrete houses help stopping this imitation of the fire? And this is, for example, Icon is a big company in 3D printed houses in Texas. They actually 3D printed 100 houses. It was the largest neighborhood in the US. It's already in Texas, built, printed on site. And there's a lot of research can be also done for roof systems that help reducing the imitation. Hurricanes, here is from Mexico Beach. I think this is Hurricane Michael. You can see here, this is an elevated house that was only survived and everything else went out of the area. And we can see, we don't have evidence yet, but how those 3D printed homes with concrete can maybe a better option in mitigating hurricane loads. So also research needed to verify that. There is also component of the layers and how those layers can prevent intrusion of water during those events. Similarly to flooding. And there is also need to verify this technique for flood resistance home. Outside of the concrete manufacturing for seismic steel systems, with the damages can actually seismic fuses and those systems that can help in earthquakes that we discussed, and hopefully other research will continue other systems. How about coastal flooding? Can 3D printing help in coastal flooding? Yes, we have artificial reefs now. A lot of companies interested in artificial reefs, and there's a lot of potential for 3D printing those reefs on the land and underwater and off water too. For hazard preparation, you can see here shelters prior to hurricane. We have signs of hurricanes that we can evacuate. Can we actually 3D printed modular units that can be assembled away from the site of the hurricane path? And this is actually a project that we have, but I don't have a chance to present it today. It's actually a modular 3D printed walls that integrate all the utilities in it using foam for insulation, lighting system, window opening, and integration of pipes that we published last year. With that, I want to acknowledge our collaborating partners and funder agency from Department of Education to Henry M. Rowan College of Engineering for the funds for startup and equipment, funding from US Army Corps, AISC, collaboration with NEST in a lot of work on 3D printing of concrete structure, companies like Sika, 3D Potters, the 3D printing company, Vivid Tech and ESP for the metal 3D printing. With that, I want to acknowledge also our research group, our student at Rowan University for all of this nice work that we do at the university. And I'm happy to receive any questions, and thanks for tuning in.
So the work question, or at least one I saw, of course, that process. Okay, so see the question, you could read it yourself and answer. Or anonymous.
So questions are going to be entertained by entering them into the chat time.
Yep. So if anyone has any questions, like I said before, enter them in the chat or the Q&A. We'll go through them.
I don't know if you all heard that, but if you have any questions, except here in the audience, if you're on the virtual link here, you should enter your questions in the chat. And
okay. So the first one,
the speaker here. So let's see. So you're on the hot seat here.
Okay. So the first question is what was the nozzle size or diameter that's used for printing your columns? It was 1 inch nozzle.
Easy question.
Yeah.
We'll leave it open for a little bit and see if anybody replies.
Sure, I got a question here. Yeah, so, the metal printed fuses, any concerns about, the size effects on the performance, right? Those were very small fuses that you printed.
Yes, so the question was, what is the size effect of the 3D print fuses? In an actual building, this fuse could be longer, it could be like 15-inch long. We try to make it between 12 to 24 to basically allow a lot of businesses to be able to print those fuses. For the size effect, the only thing I can think of is more imperfections that could happen in the large scale. And also the way that we do the heat treatment of this element, how they can maybe warp around in a small scale versus large one. We did not yet test the large one. The only one we tested was to verify the compression capacity. We want to have like a kind of stable post-buckling behavior.
Sure. Okay.
We actually did also some research, but it's not yet presented. We have a couple of pending paper on those. Numerically, try to make more fuses that have like symmetric behavior. So you have the function side and the compression side symmetric, similar to buckling restraint braces and other type of braces too. Sorry, fuses too.
So the plan is when you do later down the road, when you do larger scale testing, is to use something
that is
full scale.
Yeah.
I had a question about your FEM analysis, panel analysis that you showed. I don't know if you want to bring it up on the screen.
Which one? On
The experimental versus the FEM.
Yeah.
The two curves that are on the same plot.
This one.
That's what happened to it. It was about the middle. Oh, okay, that one. So how did you this the analysis was before the experiment or the experiment to be
this was the analysis before the experiment.
This analysis for experiment.
It's applied, yeah.
So what do you think you attribute the difference to? Because what I noticed right away is the elastic stiffness, which can either be the Young's modulus.
Yes.
Or maybe the thickness of the material. Have you gone back and tried to analyze this?
We did not. We did the SEMs to see what kind of imperfection we have, and we do have some uncentered elements or not fully melted particles that may create voids, and that actually could contribute into the high stiffness in the finite element compared to the actual test. We were not able to quantify it because we don't have the history of the print as we printed. However, we do have the digital image correlation data. And our goal now is to go back and understand the strain and stresses and correlate that to the numerical model.
Yeah, we tried to do mechanical testing to try to quantify the material properties.
Yes, this is a plan, but for the model we use the fabricator stress trinker. So the fabricator has set of stress trinker for duck bones using this technique, but our shape is not a straight like a duck bone. It has a lot of contribution, and we also do a bead plasting to remove the dark heated outside. And we asked them how much you guys removed, and we tried to incorporate that in the model after, but this was prior to testing, so it's applied production.
Yeah, I can't quite tell which line is which. I'm just going to assume that
the red
is FEA.
The steeper is the model.
the steeper is the analysis.
Yes.
Yeah, that's sometimes typical analysis, but yeah, I mean, that could be rather important because if you're going to have design methodologies, you have to be able to certainly do elastic analysis.
Yes.
Right. And so it could be, again, the material properties or the even be the discretization, but it'd be interesting to try to resolve that. But it seems you have to also get the mechanical properties.
Yeah.
That's elastic buckling when it fails, or that's inelastic buckling.
This thing is
like it's almost bifurcation.
it's inelastic.
Yeah, because it's rounded.
Yeah.
Okay. And not all of the, I'll just call it the legs buckle concurrently, so there's
All
probably
the, all the stuff, yeah, all the, for the double funnel, the lower side buckle without the top one. And the second specimen is only the top one tested. So we machined it, removed the damaged plates and tested again just to verify. We were scared that this maybe when testing a second time that we have less capacity and we cannot justify it, but it was like 5% extra on the high rates. We actually tried now to apply for funding to, instead of just optimizing the fuse and printing it, actually print different loads, apply, using it for compression testing, tension and low cycle fatigue, understand the material in the material level before we go to the fuse stage. So optimization of material processes, because a process affects the material affects the process.
Okay, yeah, that,
Check it. You want to drive it? We can see if we have any. Just go to the top
Okay.
and then see.
Yeah. So I can see another system connected to your 3D printer. Do you recommend an extruder pump or the show auger system for 3D print? Any minutes for the auger extruder pump. So the question is like, what is the difference between the extruder pump, using pump to extrude right away to the nozzle versus using an auger? We have both in our laboratory. We prefer auger system because we have a lot of control on the extrusion rate. So we use the pump to just deliver the material to the auger in a good rate and control the extrusion through the auger. If you have a very sensitive pumping system that you can control, that could also substitute the auger. So it's based on your situation.
That's it.
Any other questions from the audience? Give them a minute. It could be a little bit latency in the internet.
Are those videos of the printing real time? Is that how fast it goes, or is that sped up?
I think it's actual speed.
That's interesting.
If we do have the speed up, we put like 2x or 4x.
Yeah.
Yeah. So coming back to my favorite topic, reinforcing
Yes.
in concrete, that's a major concern of having reinforced in the main concrete.
Yes.
Right. So if you looked at it, maybe having another type of material that
Yes.
analogous to concrete that has much better tensile strength,
Yes.
right? Because reinforcing is
So
not really going to work too well.
exactly. So we always try to say, okay, if you go back to history on reinforcement, the way we use rebars and stirrups are because of the formwork, right? So we are limited by our formwork and labor, right? Ability for laborers to produce those reinforcements, right?
Mhm.
So I have opinion that we should not rely on those for 3D printed structures, rebar and stirrups. You have to develop our own reinforcing technique. And that could be substituted by inline printing of wires as we print in the matrix. Or it could be a post-process with wrapping, with RB, wrapping to increase the confinement. There's a lot of options. What we do in our laboratory, we do use robotic to place reinforcement as we print. And based on our experience, the bond between the 3D printed and reinforcement is not the best. So we have to create cavities, place reinforcement as we print, and change the freehold in the material and make it flow to fill those cavities. I think I showed that in one slide briefly when I
Increase the carbon footprint.
yes,
What about post engineering?
or using post tensioning as a post process. But this is a very hot topic that the industry didn't figure out yet. Most of what I see is printing the forward, placing reinforcement casting and post process, and that will the increase of carbon footprint. This big picture that we have here, we actually inline as we print this shape. Let's say we are printing an eye shape. We create a cavity. We have robotic arm aiding construction that places reinforcement. We change the rheology of the material and fill it up. Because there's a lot of research need to be done on the bond between just placing reinforcement around the 3D print or over the 3D print, because the idea of the bond is to encapsulate the rebar. So we are actually working on different techniques now. There is post-tensioning is one bit easy solution, but with the robotic construction, we need to have a lot of good options for reinforcement. But I didn't see the rebars and stirrups as a solution for this.
Have you worked much with metamaterials?
We worked with metamaterials in the sense of exploring printing different alloys in metals. So the printer itself, you can have now each layer different material.
Have you done any testing and
Not
done
yet.
with the mechanical problem?
Not yet. We are exploring it now, but not to a stage that I can present.
What kind of materials?
So we are using for that stainless steel, titanium, and nickels.
Nice and expensive.
Okay. Well, let's see, I think we have a
I don't know, I think that might have been it.
silent group here.
Slide up.
Quiet group.
Hover up. Yeah,
I
that's
don't
it.
think
So
other
we
questions.
get we can conclude then at this point. So 5 after 5.
What type of question?
You want to
Terry, any questions?
Final
You guys
remarks.
are quiet over. Leanne? Professor Reich, you have any questions? I saw some water in the coast there.
Yes, I saw that. That's a very interesting and promising approach, especially for the rehabilitation of structures that are progressively aging and in need of reparation after an extreme event, for example. So I understand there are still challenges to do underwater printing, but that's definitely something super interesting to explore in the future. And my main question, but this is just due to my lack of experience on using 3D printers, is how easy, or better, how challenging is it to control the stereotypic behavior of the material that you print?
Control what?
How do you control the stereotypic behavior of the concrete that you print? Is it relatively easy that you impose a stereotypic curve that you want your material to behave, like controlling more or less density, how you reinforce it? How does it work?
So we are not using for our research any material that is not from manufacturer. We develop our own materials from scratch. So we also always say our research from dust to dust, so from the powder to testing to recycling. I would say everything goes to the mix design. So you have to have a good printer for sure, and good ink, which is the mix. And to develop a good printing material, you have to select the right aggregate size. So for example, bigger aggregates sometimes just clog the nozzles and erupt the flow. However, in the market now, there is actually printing with very large aggregates. It all comes to the density and the flow and the printing parameter from extrusion to speed of the print. So based on our experience, we have been spending like 8 months alone just to develop our own material. I was challenging a lot of failure, but once you tune it, I think it's very repeatable with us.
So how much uncertainty in rendering this is it be given material and designer wants efficacy of this and has something in mind, and certain manufacturers go out and okay, I'll print your structure for you. How can you rely, or what's the uncertainty of cultural variation?
So
properties?
for the houses, that maybe our material is not a scale of printing large stuff like large houses, because I need to resource the material and sell it. However, in a scale of using like commercial mixes, the safety factor are very low. So like 0.6, 0.5 as of now in terms of the fee values. So there's a lot of uncertainty, as you said.
It's a
They reduce the fee factor,
the fee factor.
So the fee factor is
Resistance factor is 0.65.
0.6 or 0.5, even 0.5, sorry, 0.5 or 0.6, 0.5 or 0.6.
0.5 or 0.6.
Yeah, so it's a way for those businesses to prove the concept. They're going to be bigger in size, going to be maybe not the most economical, but as more research is going right now, the refinement of those factors will be enhanced. A lot of companies rely on it as like masonry structures, printing layer on top of a layer and using a lot of masonry equation, which doesn't actually translate. One thing we didn't discuss today is now you have a research also in optimizing the printing path and actually printing different layers in different direction. Now you can actually, within your structure, lay out your printing orientation to defy some stresses and better resist the stresses. But yeah, there is potential, but still early age technology.
It's just a very naive question. Like I'm familiar with your typical PLA type printing for toys and grass and toys and stuff. But is that use a slicing method too?
Yeah, you have to have this slicing software. So you have a CAD slicer, a lot of dry testing to verify it, and after that deploy it. So whatever video I'm showing today is behind the scene. There's a lot of buildability issues until you reach the stage.
Is that something you guys develop in house, or is that a marketing? Is that off the shelf that you buy a slicing software for a company?
Actually, we are using some of us use Cura or Simplify 3D too.
Okay.
So we are using Simplify 3D.
Okay.
Is anyone working on microgravity 3D print?
Microgravity, we do not yet. Hopefully in the future. Yeah, we have this idea. We have,
You can't get houses up there.
yes, yeah. We're rolling out application. Marshall's construction. Not yet.
Okay, so no other questions.
Let's check. Want to slide
Yeah, I
down
mean, we're a quarter after.
Yeah, we're gonna be good, so we can conclude, Jim. If you want
Okay,
to thank
well,
your speaker.
wanted to thank the audience, sorry. So I want to also thank the speaker, but you get thanked after the audience. So I wanted to thank the audience for attending and also in person, but also by Zoom. And so we're going to go ahead and conclude our presentation and thank the speaker here. Very nice, very informative. And I mentioned that this is archived. It may take a few days or so.
Yeah, about a week. We'll get this up on our Lehigh Design Safe website if anybody's interested in revisiting it.
Yes, and I think it's under resources, is it the pull down tab or?
It's outreach, it's called outreach.
Oh, it's under outreach.
Yeah, so
Okay, so if you have any questions, you can
feel free to contact
us.
any of us.
Our contact information's on our website. That's
All right.
easy to find.
Sounds good. All right, thank you all. Take care and enjoy your evening and rest of your
Thank you
days.
very much, everybody.
I think the natural progression here was having to do